So I was talking about the need of a vector as a tool for understanding the electromagnetic forces and the various interactions and all. So let us start with the vectors. So what is a vector? Vector, as you see that we can represent any physical quantity like temperature or force, gravitational force, or using some mathematical tools. So when it comes to the physical quantities like force, we will be using vector as the tool, and when it comes to the physical quantities like temperature or pressure, we will be using scalar as the these are all scalar quantities, we can say. This temperature and pressure, such kind of things are the scalar quantities, whereas the velocity or the forces, all these are the vector quantities. So in analytical way of representing a vector is we will be using some notations like. So in the vector analysis, first we will see how to represent a vector. Let us assume that there is a vector A. So whenever we use a vector, we will be using this notation, this arrow on the top of this vector, this arrow. So and usually in the textbooks and all, you will be seeing the bold face letters to represent the vector without arrow. So but in the notes and all, we will be using a capital letter with a arrow on top to represent a vector. So if you consider there is a vector A and if there is another vector B, so there are two vectors. Okay, so let us also draw these vectors separately in a two-dimensional image. So let us see, there are x-axis and y-axis. So let us assume that this is your x-axis and this is your y-axis. If you wanted to represent a vector, like for example a vector which is originating from this origin to one point P, let me assume that this point P is maybe 1 and 1 in Cartesian coordinate system or in the rectangular coordinate system, then we can say this vector A can be written as 1 in the x direction, 1 in the x direction. So direction, we will be using the notation x cap, or sometimes we will be using the notation ax also for the directions. So let us now use the notation x cap here to notate the direction. So one unit in the x direction and another 1 unit in the y direction. So naturally this equation for this vector will be x cap plus y cap. Suppose for example if this value is instead of 1 1, if this is 2 and 1, then the representation of the vector will become 2 times in the x direction plus 1 time in the y direction. So this is how we will be representing a vector. So if there are 3 dimensions, like for example in Cartesian coordinate system, we will be having 3 directions, x, y and z. So in 3 dimensions when you represent a vector, so again we can write it as vector A is equal to suppose 3 times in the x direction plus 4 times in the y direction plus maybe 2 times in the z direction. So now here what happens is these values what you are seeing here, 3, 4 and 2, which can be represented in terms of the variables again. So we will write it like vector A in general form, we can write as Ax. So here Ax is equal to 3 x cap plus Ay, the y component, which is 4 in this example, plus Az z direction. Okay, so this is how we will represent a vector in the 3 dimension. This is the general representation of a vector. So similarly, if I write another vector, vector B, for example vector B, which is can be written as Bx x cap plus By y cap plus Bz c cap. So now this Ax, Ay and Az can have any values, which is ranging from -infinity to infinity. Similarly, Bx, By, Bz also can have any values. So depending on that, like that we can represent one vector. So now when it comes to operations of the vector, so let us now understand what are the vector operations. Okay. So this vector operations are, there are many operations, like we have a vector addition, then we have vector subtraction, later we can also think about vector scaling, I mean the increasing or decreasing the magnitude, that is called vector scaling. Okay. Then we can say vector rotation. Okay. Then we have a vector multiplication. Okay. Okay. Then there are integration, differentiation, all these vectors also possible. Anyway, so when it comes to the vector addition, it is basically, suppose if you have two vectors, vector A and B, I told, like, let us take one example, vector A. Okay. This is vector A, let there be another vector B. Okay. Another vector B. So when you add the two vectors, basically what we will be doing is we will be doing the addition in this way, right? So this is the resultant vector. Let me call resultant vector is M, the vector M. Okay. So let me, when we write it in terms of Ax, Ay, Az component, we will be saying vector A is equal to Ax x cap plus Ay y cap plus Az z cap, and vector B, as we said, it is Bx x cap plus By y cap plus Bz z cap, and the vector M, the resultant vector, which is the addition of vector A and vector B, which is now what we will be doing is we will take the x component and add, and y components and add, then z components and add. Only the x component, if you add, it will become Ax plus Bx. These are the x components. So when you will only add these two and assign the x direction to this, then y components, which is Ay plus By, again assigned the direction y, and the last thing is Az plus Bz, and assign the direction Z. So this is how you will be adding it. So if you are able to add it, the similar logic is applied for subtraction also. So instead of this plus symbol, what you can see here, instead of this plus symbol, we will be using the minus in case if there is a subtraction required. So this is about vector addition or subtraction. So what we seen here is basically the vector addition or subtraction. Okay. Okay. Now when it comes to the next vector operation, that is the vector scaling. So scaling of the vector means, okay, scaling of the vector means we will be multiplying a vector with a scalar, multiplying vector with scalar. Okay, this is what is called scaling of the vector. So when you multiply a vector with a scalar, what basically happens is, suppose if you consider there is a vector in one direction. Okay. So if this vector, if you are multiplying with a scalar, what basically happens is the direction will not change, but the magnitude will either increase. This is like when you are multiplying, if the multiplication factor is more than 1, magnitude will increase. If the multiplication factor is less than 1, the magnitude will reduce without changing the direction. Direction will be the same direction, only the variation will be having in the magnitude only. This is what happens when you scale a vector. So in order to do the scaling, basically what we will doing is we will multiply with a scalar, means suppose if there is a vector A, which is now defined as in previously we have written Ax x cap plus Ay y cap plus Az c cap, and if there is a scalar which is represented by maybe alpha. Okay. So I will be multiplying alpha is a scalar, then multiply with a vector A. Okay. So the resultant of this will be also another vector, but every component of this, every components like Ax, Ay, Az, all these things directly will get multiplied by the alpha. So you will be getting alpha Ax x cap plus alpha Ay y cap plus alpha az z cap. So here that's what I said. If alpha is greater than 1, it is basically increasing the size of or increasing the length of the vector, we can say, keeping the same direction. If alpha is less than 1, it is basically shrinking that vector in the same direction, but the direction will not change. So now this is about the scaling. We will also see how to represent the direction of the vector later. Once scaling is done, the next operation is vector rotation. Yeah, the rotation of the vector can be done by multiplying a vector with a matrix basically. So suppose if you take one vector A, okay, let me take a two-dimensional vector so that it is easy for us to do that here. Let vector A be 2x cap plus 3y cap. This is the vector A. And if you see this vector A can be, now you can draw this vector in the rectangular coordinate system by keeping this as your x-axis and this as your y-axis. So 2 plus 3y means like you will be having in x direction 2, 1, 2, 3, 1, 2, 3, 4. So 1, 2, x direction 2 and y direction is 3, right? So you will be getting the point is somewhere here. This is the point, okay? So this vector what I am drawing right now, okay, this vector is your vector A now, okay? So now when you do the, in order to rotate this vector, rotating that vector can be without changing the magnitude also. So when you rotate the vector without changing magnitude, for example, what you need to do is this is one vector which is represented as 2, 3, right? So let me write that vector in the matrix form, that is 2 and 3, okay? 2, 3. So now what you need to do is, in order to rotate the vector, we need to multiply with a matrix. So since it is a two-dimensional matrix, so we will multiply with a 2 by 2 matrix. So what will happen is, let us take one value, that is 1, 0 and 0, 1. This is the matrix. So what happens in this case is like 2 into 1, that is 2, plus 3 into 0, that is 0, and then 3 into 1, 3, 3 into 0, right? 3 into 0, 0, plus 3 into 1, 1. So when you do the this is 3, 3 into 1 is 3, right? When you do the matrix multiplication, you are naturally getting the same values, right? That's what we are getting. So 2 and 3. So now if I put 1 and 1 here instead of, so we will make 0, 0 here and 1 here. So what will be the answer you will be getting is basically 2 into 0, 0, plus 3 into 1, 3, and 2 into 1, 2, plus 3 into 0, 0. So you will be getting 3 and 2. So basically what is this 3 and 2? This is another vector which is getting rotated. So yeah. So now what I wanted to convey is that, or we can say that the rotation can be done. So rotation of the vector is another operation, as I said. Rotation of the vector is possible by multiplying that vector with a matrix. Okay, this is possible by multiplying with a matrix. And now let us also see the last operation, that is the vector multiplication. So when you talk about this vector multiplication, we have two types of multiplication. So let us write vector multiplication. Okay. So there are two types of multiplication. The first one is the dot product or scalar product. Scalar product. And the second one is cross product or vector product. So when it comes to dot product or cross product, we will be multiplying two vectors. Scalar product will do inner product, we can say. So scalar product or scalar multiplication and scaling are two different things. Okay, scaling means we are multiplying with a scalar value, but scalar product or dot product means we are multiplying a vector with another vector. Okay, so when it comes to dot product or scalar product, if we consider two vector A and vector B, okay, the dot product of two vectors can be represented using A dot B. Okay, so basically in this dot product, what is the way of representing this dot product is, it is basically to find the projection of a vector on another vector. Basically, dot product means projection of the vector on another vector. So when it comes to two vectors, for example, if I consider this is vector A and this is vector B, okay, this is A and this is B, dot product will basically give you the new vector, which is this vector. The suppose if this is vector C, then we can say C is nothing but vector A dot vector B. So suppose if this is the case, let us assume this angle between this A and B is theta, then you can easily say that this vector C, the magnitude of this vector C is equal to the projection of this A on B, or we can say in another way, suppose if we have a magnitude of the vector B into magnitude of this vector A, or other way like magnitude of A into magnitude of B into cosine of the angle between A and B. So that is the representation of a dot product, and here we will be able to use this kind of dot products concepts when it comes to various applications like as divergence. Yeah, so we can use that dot product here, and yeah, let us take one example. Let us assume that let vector A is equal to 3x cap plus 4y cap minus 5z cap, and vector B is equal to maybe minus 12x cap plus 24y cap plus 3z cap. So how do you find the dot product vector A dot vector B? Basically, we will be taking the dot product of the component vectors. Okay, so when you take the dot product of the component vectors, for in this case we have to write it like 3x cap dot minus 12x cap. That's the first case, right? So plus 4y cap dot 24y cap plus minus 5z cap dot 3z cap. So this is your equation. So now if you see here, now we can see by the definition of this dot product, we know that vector A dot vector B is magnitude of the vector A into magnitude of the vector B into cos theta. So let us now consider the first case is the first element, this element let us take. Okay, so in this element we can see that 3x cap dot minus 12x cap, this is what is there, right? So I can take this 3 and minus 12, right? 3 into minus 12, 3 times minus 12, then we can say direction part is only x cap dot x cap. So 3 into minus 12, it is minus 36, right? And what is x cap dot x cap? So as per the definition of this thing, it is magnitude of A into B into cosine of the angle between. So when you consider the direction vector has a magnitude of 1, okay, and the angle between these two x cap and x cap. So if you consider x cap and x cap, 2x cap, the angle between that is 0. So that means the cosine of 0 will become 1 there. So this entire term will become 1. So that means you can say this is equal to minus 36. The first term is equal to minus 36. Similarly, if you take the second term, you will be getting 4 into 24 and y dot y is 1. So 4 into 24, how much is 4 into 24? It is 96. So you will be getting 96 for the second term, and for the third term you will be getting minus 5 into 3, that is minus 15. So you will be getting an answer minus 36 plus 96 minus 15 as the answer of A dot B, which is equal to how much? 96 minus 36 minus 15. So the answer will be 21. So this is how you will be finding the dot product. And now when it comes to dot product, you should also remember one thing, that in this vector multiplication, the inputs, both the inputs were vector quantities, but if you see the output, it is a scalar quantity. So the output is a scalar quantity, inputs are two vectors. So that is why it is called scalar multiplication. Okay. So output will not be having any direction associated with that. So now comes the second multiplication, that is called the vector multiplication. Okay. So in vector multiplication, we will be multiplying vector A and vector B in a different way. So we will call it as cross product. So the notation for cross product is like this: vector A cross vector B. So in this, basically what happens is, we will be using the standard definition of the cross product. That means the standard definition says that it is equal to magnitude of vector A into magnitude of vector B into sine of the angle between A and B, and the direction of the resultant or this answer, the resultant vector, is a direction which is normal to both A and B. So this is how the definition of the vector multiplication or cross product is. And now when it comes to implementation of this, suppose as we said, if there are two vectors, vector A and vector B, with the component vectors Ax, Ay, Az and Bx, By, Bz. Okay. Now when you do the cross product, what you will be doing is, let us take one A cross B. How do we write is, okay, we will be writing like Ax x cap cross Bx x cap, right? Then the second term, that is Ax x cap cross By y cap, right, into Ax x cap cross Bz z cap. So if basically what I am doing here is, I am taking the first component and multiplying with all the three. Then take the next second component, take the second component and multiply with all the three. Take the third component and multiply with all the three. So you will be getting basically 9 terms like this. So when you do that, I mean the same thing was even applicable to the cross product also. What happened here is, the same thing was applicable in the dot product also. So basically you take the first term, multiply with all these three, okay, find the dot product with all the three. So when you do the dot product of 3x with this minus 12x, you got 3 into minus 12 was the answer, because x dot x is 0, sorry, x dot x is 1. But also you need to ensure that you were multiplying with this also, as well as this also. So there were 9 terms actually. But what happened is, like when you take the dot product of this term and this term, what happens is you will be getting the answer as 3 into 24, 3 and 24, that is your 96. Then x dot y. So x dot y, when you calculate, x is in one direction and y is in the 90 degree ahead, other direction, right? So this is x direction, means this is y direction. So the angle between x and y vectors are basically 90 degree. So if the angle is 90 degree, then the cos of 90 degree will be 0. So the value cos of 90 will become 0 there. So that terms corresponding to the dot product of this and this will become 0. Similarly, the dot product of this and this also will become 0, right? So that means only the dot product of this will be remaining. Similarly, dot product of this and this will become 0, as well as dot product of this and this will become 0. So only the remaining will be this much. Similarly, in this third case, this only will be remaining. So that means there are nine components at the output, but finally the remaining 6 components will become 0 and only 3 components will be getting it. Similarly, in the vector multiplication also, when you do this, okay, let us see what happens. Or in the cross product, when you do this, let us see what happens. Okay.